Okay, sure. So I'm going to be continuing our talk about associated points this week. So last week we talked about, well, we gave you an introduction to associated points and we described, some geometric ways to think about them, right? And so Vakil gave kind of like 3 kind of geometric ideas, and then you can prove a bunch of things based on that. But instead of talking about that a little bit, let's just, because for me personally, I just like to have a definition and then kind of like go off that. And so we're going to try and, I guess, we'll kind of look at what happens algebraically and then kind of generalize geometrically, which is kind of what we've been doing the entire time. So let's fix a ring R, always be Noetherian, and a finally generated R module, let's say M. And so our goal to start is kind of, well, we want to study M. And so what are some of the ways that we can do that? And so we really know that if you can, understand, let's say, so if you look at all the primes in spec R, and then you can understand the localizations of this module MP, then you can get a pretty good understanding of M, right? So you can determine if elements of M are 0 by looking at this. If you had, so if we had a map of R modules between phi, then for every prime ideal, you always get a map phi p. And so you can check things locally, like whether or not this map is injective, surjective, etc. But so, if you look at all of spec R, that might be complicated. So our first step is to try and find a finite set of prime ideals that really shed light on the structure of M. So that's a goal. So that, let's say, relate to M. So if you have a finite set, and then if you had a ring map, and then ideally you would be able to do similar things, like for the local case, like that. Maybe your finite set of prime ideals should be able to tell you something. If you knew about all these localized maps, then maybe you should know something about the map in general. And then since there's finally many, if you actually had this, then you could actually just do it. Okay, so this. So this set of prime ideals will be called the associated primes of M. And so we'll recover this notion, or so if we had just a scheme now, or an affine scheme, then the associated primes will be the associated points will be the associated primes of the overarching ring as a module over itself. And so let's take an example, let's take RZ, take M is Z mod N, and let's say we factor N like this, right? Then the associated primes will just be the prime divisors of N. Maybe another example quickly. So let's try something more geometric. Let's take X to be I think we looked at this last week here. So here I'm thinking of this geometrically. So now when I say the associated primes of this, so we'll write it like this. So this should be in this case, you'll end up getting, looks like this, and you can kind of see what this looks like from the picture, right? So this is this, and so the associated primes are just the x-axis plus this stuff at the origin, which is supposed to be like picking up a little bit of this infinitesimal fuzz that's going on there. So one of the ways that you can kind of think about this is that the associated primes, they're often really related to questions about reducedness and things like that. Okay. Because let's just see what they are. So again, R Noetherian, M finally generated. So an associated, let's say, prime of M is a prime ideal P such that P is equal to the annihilator of some M, some element of M. So that's what an associated prime is, and then the SAM, the collection of associated primes. So if we go back over here, if you think about what would it mean here, so how would I get that the PIs are an associated prime? So maybe I would take something like, when I say it was D, J. Or like this, if you look at the annihilator of this, it's just going to be P. So that gives you all of them, and by thinking about that similarly, you'll find that there can be no other primes that could annihilate any element in M.
Those aren't any other primes. Those are all the prime ideals, is that right?
Yeah. No, that's also true. Yeah.
Well, it's prime ideals of the ring.
Yeah. So it's prime ideals of R, right?
Sure. Yeah.
Because usually, I mean, not always, but oftentimes, if you just look at the associated prime ideals of, if you're looking at something like this, so if if A was a domain, right, so you're in a good situation, then what are the associated primes?
Just zero.
Yeah. So you have that it's just zero. So there's just one thing sitting there. We can actually also see that by thinking about some like the geometric intuition. So I think what did Vakil say? He said that the associated points should be the irreducible components of the vanishing of sections, right? So if you looked at if this was a domain, where do sections vanish? Well, they're only going to that. So if you look at the only irreducible component you're going to get is just zero itself. And then here, I mean, if the types of things that you would do is, okay, well, what would be, I mean, there's two special elements to look at. Like, what is the annihilator of, what did I say? Did I do x? What is the annihilator of x over a? So what does that mean? That means that I have to have some polynomial fxy x has to be 0 mod I. Right, but that means that I can write this here, that xf is equal to x squared a plus xyb. And so you can just divide out by x here, and then you say, and then you're seeing that. So f is plus yb. So f was in xy. And so similarly, anything in xy annihilates x, so we see that that xy is an associated prime. And then similarly, if you looked at the annihilator of y in here, then you would find that what you got was just x. So what's the big result, or the first big result? And so we've done a little bit of this last time. So let's say theorem, let's say, so again, R Noetherian, M finally generated R module, A. The associated primes of M is a finite, non-empty set of prime ideals of R. Furthermore, we can say something about the prime ideals that occur in here. So each contains the annihilator of M itself. And let's say the associated prime contains all prime ideals minimal. So if you want to find an associated prime, you could find a minimal prime ideal that contains the annihilator of the whole thing. B, so I take the union of all associated primes. So this is 0 divisors on M. Well, let's say delete 0. Well, I should delete 0 from here. And C, we talked about it last time, but I guess it's important that the construction of, let's say, SM it commutes with localization. And so part C here, this is what allows us to but it gives us a convenient way to describe what the associated primes of a given, let's say, locally Noetherian scheme. But so what is this? Explicitly, this is saying that S, let's say, S multiplicative in R, then that this is equal to and so this is C. So this is kind of this is maybe the first result that is really proved about this. And so I'm not going to do it. I mean, if you're interested, it's in Eisenbud. That's where I first saw it. It's reasonable. But so what can you get from this? I mean, already this is kind of, nice, but let's say we have some corollaries. So let's say A. So if I take M in N, then M is non-zero if and only if MP in MP, right? Is not zero. So if we were looking at something, maybe we were thinking about a case like, something, maybe XYZ mod I, you have some relations here, and then I just gave you a polynomial, just some polynomial, and you basically want to know, is that polynomial in I, right? If you computed the associated primes of this KXYZ module, then you could just check in the localizations whether or not that was zero. And sometimes it's just easier just to work in the local picture. So B, this is just a direct extension of A. So you have K and it's an M, let's say, submodule, right? So then so you could check if a submodule is zero, and C, if you take a map phi from M to N of, let's say, R modules, then we can check injectivity locally at the associated primes. So just by getting your hands on the associated primes, you're able to do some things. So it's kind of like just some tools in our toolbox. So I guess that's most of what I'm going to say about the algebraic side of things. And so now that we know what's happening just locally on an affine scheme, now we're going to talk about what happens if I just go to to a general locally Noetherian scheme. So what do you think? What's the definition going to be? I mean, did you define what they were? Okay. Well then good. So let's say x, right? So let's just say the associated primes of the structure sheaf, right? We'll just define them like this. So it's so it suffices just to look locally. You take a point, look at the local ring there. That point corresponds to the maximal ideal of that local ring. You check if it's an associated prime. Now, I think that maybe it was last time that you don't have to necessarily look locally. You can do this with the chart as well. You could just say, so if you had an affine open chart of x, then let's just say x in spec AI. And associated points. If let's just say x, this is the prime ideal corresponding to x in A, or AI. So right, and so why is that true? Well, this is where you use this here. That if you think about what is happening, then here S would be AI. You throw away the prime ideal corresponding to the point X, and then you localize. And so this is how you can always just, check locally. And so we were able to define this just for any locally Noetherian scheme, but if we were actually Noetherian, right, then we see that I shouldn't have erased that, but we see that we actually get finitely many associated points, right, because we just have, if it was Noetherian, then there's finitely many of these, and each one is finitely many points, because all the AIs are Noetherian. So let's say, I don't know, remark. You have finitely many associated points. Okay, so now we know what the associated points of a, let's say, of a locally Noetherian scheme, we can start talking about, we can start talking about rational functions on that scheme. And so I think that earlier we know what the function field is and stuff, I think, but we don't really need to go too much into it. And honestly, I don't think that we'll be using rational functions too much moving forward. We'll be using rational maps, more of a thing maybe. But let's do it. It's easy to define. So given, let's say, define definition. The ring of rational functions of a locally, let's say, Noetherian scheme. So let's just is the collection of, let's say, pairs UF. U is open. It contains all the associated points of X, and F is a section on U. And just like when we constructed the local ring, we put an equivalence relation on this. Right, we say that two such pairs are equal if there is some open set containing that is contained in both of them. Well, maybe let's write it. So there exists, let's say, V, and so the V now also has to contain, right? And then we just say that, let's say, V is contained in U, W. We want F restricted to V to be equal to G restricted to V. And so this is the ring of rational functions. So now we're just looking at functions that are defined on open sets that contain all these associated points. So the slogan is kind of, the associated points are, where the action happens. And so if we were in a domain, then the only associated point, it's a generic point. The generic point is kind of everywhere. So the action's happening everywhere. Right. So we could also, if you want to be fancier, you could also say that so it's what? You could say it's the direct limit of, you'll go over all open sets containing the associated points. Then you look at, right? And then if you did the explicit construction of the direct limit, you would just obtain this definition here. I don't know, let's say, example.
Where does this definition, does it mean anything about Noetherian?
So
associated points, right, in general?
Yes, but I think that to get the properties like that is non-empty and stuff, yeah, you want it to be Noetherian. Because when you end up proving it, what you end up doing is you end up looking at the annihilator of M, and then you want to choose and look at all the prime ideals contained in that, and you end up wanting to choose a maximal such thing. So I think that sometimes you will talk about it not in the locally Noetherian case, but then I've heard people say a weakly associated prime, and so there might be some more details. But they do, so for example, they do talk about that a little bit, at least in the Stacks project, right? So there's all this algebraic geometry on the Columbia website, and they talk about that a little bit, but I've never seen it actually come up. So I don't know. So I guess this quick example. How much time do I have? Well, let's skip the example. Let's just take a bigger example. Okay, well, let's take x to be spec A. So now, and a Noetherian, or so I guess I should say R because I've been using R. R Noetherian. So what are the rational functions on R? So here, so we have this definition, but so then proposition, let's say, so the rational functions of x is, let's just say, it's Q of R. And so this is the quotient ring. So what I'm saying is, I'm just saying, look at the multiplicative set of all non-zero divisors, and then you localize there. Okay? And so in that case, these are the rational functions. So how much time do I have? So does everyone kind of, so how would you go about proving this? I mean, we have this definition, and then we have this definition. And so, I mean, this kind of makes sense as the rational functions, but why is that actually?
What's the QR there?
So this is the quotient ring of R. So what I'm saying is, so do you know what I mean?
Yeah,
Okay.
R is the
R is just some ring here, right? So we're just here. I'm saying x is just spec R. So that I just have some affine scheme, some Noetherian affine scheme, and then here the rational functions of x is just the quotient ring. So just to give an idea about why this might be true, if you were using this definition, you're dealing with elements that look like this, right? U contains the associated primes. And then it's oftentimes much easier, because we want to get to a localization. What's the easiest type of localization? It's just localizing at some f, right? So what would really be nice is if I could write something like, this is really, let's say, dg, and this is like, right, that these are the same. And so you can do, and then once you have that, then it's relatively straightforward just to piece together why that would be the case, like really concretely. But so why should this here be true? Because here, so the question is, why is there some principal open set that contains all the associated primes? And so why you would probably maybe think about why this is true is because, some people, people have like little slogans or whatever. So they'll say something that, well, if you have an affine open scheme, right? Or if you have an affine scheme, say Noetherian, but I don't think you need it. And then you have some open set that contains finitely many points, then you can always reduce to a smaller principal open set that still contains those finitely many points. But why can you do that? And that's really the whole prime avoidance thing, right? So, And so that's actually, you know, kind of precisely what's happening here. Right here we have, so the idea would be you write U, you cover it with these principal open affines, these distinguished open affines, right? And then we say, let's say, P1 are the associated primes, and say, let's say that Fi is not in Pi, so what I'm saying is that Pi is in dFi. So you take the first, let's say, you take T of these, and then you have, so now you let capital I just be the ideal generated by this. And so then we know that I is not contained in Pi. So what this really means is that, so this implies that, right, this is the prime avoidance lemma. And so then you take some element that's in here but not in here, and you use that to construct a principal open that is contained in U and also contains all these PIs. And then from there, you do a little bit of work, and you can show that these two things are the same. So at least in the case of an affine scheme, an affine Noetherian scheme, the rational functions make sense. And if you want to go now, if you want to go to any scheme, then that gets a little bit more complicated. Let's skip that. So what one can do is that instead of just looking at the rational functions, you try and look at some similar sheaf on a scheme X. And so if you really do this formally, you get, let's say, the sheaf of stalks of, let's just call this meromorphic functions on X, and this is donated Kx. So what's the idea? And so, I mean, why do you care about this? I mean, so if X was Noetherian, if X was irreducible, we'd be doing all this, and then this would just be the fraction field, right? And so it would just be some constant sheaf, and the same thing would happen here. But if you want to kind of try and start doing things that you usually do when you're with a scheme that is not necessarily irreducible, then you end up then one of the things that you may have to deal with is with some object like this. So what's the idea, just briefly? How would this thing arise? Well, you would just, on affine opens, you have, let's say, spec A. You just basically construct a sheaf that just looks like, and we'll call it K prime for a second, that K prime of this should just be the quotient field of A. But you have to be careful. So this is really a pre-sheaf, and so then you have to do something, and so then you have to sheafify to get this Kx. And like, why do we even care? Why am I even talking about this? Well, and the only reason I'm really talking about this is because you've ever heard about things like the group of Cartier divisors or something like this. That one of the kind of like the basic elements in the construction of that for more general schemes is the sheaf of stocks and meromorphic functions. So the idea is that from this thing here, you're able to kind of define some group associated to that scheme, and so from that you can start studying kind of the intrinsic geometry of that scheme. And so this thing here kind of really relates to you can relate it to the Picard group and so on, right? And so if you want to think about it, maybe one analogy is to think about this as, let's consider the number field case. If you had something like K, if you had something like this, and so one of the things that's of interest is, fractional ideals in here. And so if you start looking at fractional ideals in here, the invertible fractional ideals in there, play a role in a way kind of similar to this classical case, but I guess we don't have time to go into that. But the idea is that just from, and how does this relate to associated points? Well, that when you study this, it turns out that if you looking on open sets that contain all the associated points, that allows you to kind of get a better handle on this sheaf of stocks and meromorphic functions, and thus potentially get a better handle on this group of Cartier divisors, and so on. And then so maybe get a better handle on the scheme itself. How much time? I have, what, 10 minutes? No, 8 minutes? 7 minutes? Okay, so I guess backing away from anything about these meromorphic functions or something like this, in the geometric setting that we've talked about so far, everything is we've always been looking at something like, always been saying things like this, right? But just the associated primes of just the structure sheaf, that's really analogous to saying, well, the associated primes of a ring over itself. But that's not how there's a reason why we didn't just define the associated primes just for a ring over itself. We really want to talk about modules over a ring, right? And so part of maybe the disadvantage where we are kind of in the notes is that we haven't really talked that much about like what is the analog for modules on a scheme, right? So, but I mean, let's talk about it a little bit. Let's remedy it. And so the idea is that the associated primes allowed us to understand, or could help us to understand modules over a ring, over an Noetherian ring. So we'd want to have the analogous geometric situation. So let's say we call that, given a ring, and if we had M and a module, we constructed a sheaf on spec A, let's say called, I guess, like M tilde. And right, had the property that if I looked at the sections over df, then that was you just take the module and you localize at f. Okay? So this is kind of so in the affine case, this is our notion of a module on an affine space. And so now, when we defined schemes, we started with rings, we started with affine spaces, and we took a bunch of rings and we glued together their spectra. And so, we should try and do the same thing here. We should just take a bunch of these M tildes and then just glue them all together. And so this leads to the notion of a quasi-coherent sheaf, right? So let's just say what it is quickly. Definition, let's say F. NOx module, right? This just means that F is compatible with OX, right? And F and OX module is called quasi-coherent if for all affine opens contained in X, if I restrict F to spec A, that this is isomorphic to M tilde for some A module. So this is a quasi-coherent sheaf. It just means that on any affine open, when you restrict it, take the sheaf and you restrict it to it, it just looks like a module there. So maybe this looks a little bit complicated, but actually we've actually now done enough that with a little bit of work, what one can show, and what we will do in chapter 13 or whenever we actually get there, right? That you can actually just check this on a single chart, okay? And why can you do this? That's why there was all that time spent with the affine communication lemma that allows you to say something like, okay, well, if I just check it on a chart, then that allows me to see it everywhere. I mean, that's actually non-trivial to show that that this definition is compatible with that. You have to do some work. I think it's like maybe 2 pages or something. But that is how you end up getting at that. Or you could also, maybe it might be easier, but you could also define a quasi-coherent sheaf a little bit more explicitly, like Hartshorne would do, as functions on stalks, and then you end up getting something a little bit like this. But all this is just to say is that now I know what a quasi-coherent sheaf is, and now I can just define. If I take now, let's say F is let's just say let's say F is finite type. What does that mean? It just means that all these MIs are finitely generated, right? Now let's say X Noetherian, just so everything works out. And now I can define, just in general, the associated primes of my quasi-coherent sheaf. And it's just exactly what you'd expect. Because it's a sheaf, we have notion of stalks. You just look everywhere. You look at the stalk of F over the local ring, and then you check if the maximal prime ideal is an associated prime. So now, why is that nice? So now here, just as it is often profitable to study the category of modules over a ring to understand that ring, you often want to study the category of quasi-coherent sheaves over a scheme X. And so since we can always just pass, and locally it looks nice just like modules, the kind of all this stuff about associated primes and associated points, you can just kind of use to study the local to study locally. And I guess, I mean, just this whole thing becomes, a big deal, and more or less kind of like the second half of the book is really dealing with, they'll just become ubiquitous, right? And so it's through this that you really end up defining, the cohomology theory, right? Through quasi-coherent sheaves, cohomology of quasi-coherent sheaves, it'll become a thing. I guess that's what, chapter 18 or whatever. And that's 50 minutes. Okay.